using an elastic band in order to discover Hooke's law, and also to discover the elastic potential energy equation. Okay, so there's a few ways to do this experiment. Most people did this. They got a ruler, put it on their desk. They attached the elastic to one end of the ruler somehow, and they got it to a point where it wasn't stretched, but it wasn't loose. So it's sort of the very start of a slight stretch. And then they attached a spring scale to that. So the spring scale allows you to read the force, and the ruler allows you to read the amount of stretch. Now the amount of stretch is the change from what we would call the rest length, or the normal length of the elastic. Okay? So if the elastic is 5 centimeters long in an unstretched state, then x is not 5 centimeters, x is 0, hasn't stretched it. Okay? All right. So from this, you stretch different amounts, and you read different forces off the spring scale. 8 pounds. Got about 5 of them. Got this data. And the question was, what's the relationship between the amount of stretch in an elastic medium and the force it applies back onto, say, a spring scale or your finger or something like that? So we just call that F versus X. And when you plotted it, you got this relationship, which you know can be stated as this: F is proportional to X. To turn this into an equation, we introduce our constant of proportionality, call it K, and this is Hooke's law. Then you could easily solve for the value of K by finding the slope of this graph. And the unit is, it would be rise, so grab 2 points, do rise over run. The rise unit is newtons, the run unit is meters, let's say, so it would be newtons per meter. Okay, so that was part A. Discover Hooke's law, and then also provide an interpretation of K. The interpretation of K is that it's the number of newtons you have to stretch per meter, meaning number of newtons you have to stretch for every meter you want to stretch this this spring out. So if the K value was 2, then it would take 2 newtons. That's going to be on YouTube, you know. It's going to be 2 newtons to get that spring to go 1 meter. Want to get 2 meters, 4 newtons, and so on. Okay, part B. Part B was to find the amount of energy stored in your spring when you've got it at its maximum stretch, the maximum stretch you applied. So from that, you've got your graph. So it's just finding the area of your graph. Because you remember from grade 11 that the area of a force displacement graph gives you the work, right? Which is the energy transferred into the spring and stored in the spring ultimately. So this area gives us that energy stored in the spring. Now we can use the same principle to derive the elastic potential energy equation. So the area here will be F times X, right? But it's a triangle, so it's half F times X. But we also know that F is equal to Kx. That force is equal to Kx, which is the Hooke's law. So we have this expression 1/2 Kx squared, and this will be the work It's the area. This is the work that we did on the spring. We put energy into the spring, we transfer energy into the spring, and it was stored as elastic potential. So we can also simply call this elastic potential.
And that's how you derive that equation?
Yep.
I'm trying.
And that's it. That's the lab. So that's learning goals 1 and 2. So let's do 1 and 2.